Hey guys, so let's talk about a few of the important concepts I couldn't touch on Tuesday's class. All right, I'm currently in Philly at a conference and it's a little bit noisy, so I'm sorry for that if you don't like background noise. But anyway, momentum in two dimensions. All right, we've done a lot of problems that have our momentum in one dimension, but momentum can be in two dimensions. Yeah, and this happens when the two objects, at least one of them, is coming at an angle to collide with another object. All right, so we can look at a momentum vector's two dimensions by decomposing it. All right, anyway, let's go. So how do we attack problems in two dimensions? Well, remember momentum is a vector. So P equals mv. I can break it into its components. Px equals mvx. All right, and py equals mvy. Right. So if there are no external forces acting on my system, right, I know that my momentum is conserved. All right. So how would you solve problems? Well, I'll give you an example in class before I make this video too long. So how would we solve problems? Well, we need to solve the conservation of momentum theorem in the x direction and then solve it in the y direction. All right, p initial y equals p final y. All right, and oftentimes in these questions we're looking for the velocity in the end is the unknown, so we have to combine the two components to often find the magnitude of one component, right? So that's how we do it. That's how we do it. I'll do an example for you in class, like I said, but just keep this idea in mind of how we should solve problems in 2D. Anyway, so the next concept I'd like to talk about is the relationship, a comparison of how different angular momentum is from linear momentum. So basically, they're pretty analogous. We have angular momentum, the sign L equals our inertia times angular velocity, and we have our linear momentum equals our mass times our linear velocity. So the characteristic that has to be present on our system when angular momentum is conserved, we have no external torques. All right, and the characteristic that has to be present when momentum is conserved is that no external forces. Now, I hope you can visualize what this means, yeah? So by no external forces, like let's say this is my system right here, yeah? I have two objects coming to collide, all right? When I say there are no external forces on the system, I mean there's no force on the system that makes the system accelerate, right? If the whole system was moving in a constant velocity, that would be okay. Momentum will still be conserved, but most of the time the system is at rest. However, if the system is accelerating, all right, it's moving around, then there's an external force. Oftentimes, you can attribute it as saying the acceleration of the center of mass of the system is 0. All right. So you could say that the acceleration of the systems.
Is that Makalele?
Yes, the center of mass.
Man is studying.
I'm
right
making
now?
a video for the kids right now.
Oh my goodness.
Yeah,
Oh my bad.
You're in it. You're in it. It's okay.
Hello, kids. How we doing?
The center of mass is 0. Yeah, and then the so that was Mr. Mueller. Sorry. Anyway, so the torques about the systems, and remember, not an individual particle, but the whole system, all right, is 0. Or R0. Yeah, and our conservation of angular momentum theorem is, angular momentum initial is equal to the angular momentum final. The momentum initial is equal to the momentum the final. So this is initial and final are basically before and after events. So before collision, after collision. All right. Now, what's the difference between the two? This is really what I want to dive into. Well, with momentum, we see that m is a constant. All right, m is a constant. It will not change. So when we use our momentum theorem, let's see, our conservation of momentum theorem, we have PF, PI, going to be MVI, EI, M1, because that's a constant, M2, VF, right? Let's imagine it's one particle. So our mass here will not change at all, right? It's a constant, it's something that's inherent about the system. But if we have our angular momentum, right, Li equals Lf, we have our inertia times our angular velocity equals, so the initial inertia times the initial angular velocity equals the final inertia times the final angular velocity. So, remember, inertia is not only about the mass of an object, it's also about how the mass is distributed about a particle, or about a rigid body rather. So it can change, this can change, all right? So inertia changes, all right? So then if inertia changes, how will we keep the conservation of momentum theorem, of angular momentum theorem? Because this equation should equal to that equation, right? Because it's an equosines. Well, actually, let me derive this thing for you really quick. We know the angular velocity formula is I times omega, right? I can divide by I to get the relationship between angular velocity and inertia, and I can see that my angular velocity is proportional, inversely proportional rather, to my inertia. So what does this mean? When my inertia gets big, all right, inertia gets big, angular velocity gets small, all right? It's like because 1 over inertia, right? So if 1 over a big number will be a small number, right? And so if my inertia gets small, angular velocity will get big, all right? And that's really what I want you to think about when coming across momentum problems, all right? Anyway, guys, it's been fun. I have to go back to the conference and talk. Not talk. I gotta do some other stuff. But yeah, anyway, have a good time. Can't wait to see you guys in class on Thursday. See ya. Bye.